Good morning. Sorry about the preview thing. It's still not, haven't figured that out yet. Uh, Today will be either the last or second last day in this unit, and we have to take a look at the photoelectric effect, which is the last little bit about quantum theory that we're going to study this year. Not sure if it'll take us a period, but it might take us a little more longer. It's fairly complex. That deals with light, so you'll have to remember your physics from Physical Science 20 and that kind of stuff as well. So that's what we're going to look at today, basically the photoelectric effect. We'll wait till our blackboard opens up here, and we'll get started. There are a couple equations in there, but they're fairly simple equations. It's related to the Max Planck's quantized formula that he had with his little energy formula. Okay, so what are we going to do today? Okay, this is day 9 in Unit 4. And what we want to look at is the photoelectric effect. Okay, so we want to know what that is, and then basically why it didn't fit. It did not fit in classical physics. And what Einstein did to make it fit there, and we'll look at some examples. And that's what we'll look at today with the photoelectric effect. So basically what the photoelectric effect is back in the day, in the late 1800s, and the scientists were taking light and they were shining it on a metal surface, okay, of a particular frequency of light. And what they would observe is they would see that this would emit electrons from the metal, okay? And that they called that the photoelectric effect. And then there would be, and what they saw was, according to classical physics, the higher the intensity of light that you have, it would hit the electrons in the metal, and then they would be freed up from the metal, and then they would flow, and you'd have a current. Okay, so by theory of classical physics, the higher the intensity of light, the more electron flow you should see. Well, in this case, that didn't happen. Okay, first of all, if you had too low of an intensity of light, nothing would happen at all. Or sorry, if you that's correct. It would be nothing would happen at all. And then they also surmised, according to classical physics, that you'd have to have the light shine on the electrons and build up enough energy for the electrons to be released. And that didn't happen either. Okay, so what actually happened was, as soon as you turn the light on, if it was high enough frequency, electrons would flow right away. If it was not a high enough frequency, it wouldn't flow at all. Okay, so let's do a little diagram describing the photoelectric effect, because that's the easiest way to do these things. Let's see. Let's get this down here. So what they had was something like this. They would have, if you had a tube here, okay, so inside here they had a photo tube. This works good, like flash tube. Okay, so there's the bulb, and they had on this side here, they had a metal plate of zinc inside this vacuum chamber. This is in vacuum here. That's what that bulb means. So this would be it. This was the cathode. And then they had a little anode here. Okay, and then they hooked it up to a battery. Okay, and so they'd have some current, they would be having some battery there, and then they would have an ammeter, I forgot the ammeter, to see what the current was. Okay, and what they do is they would shine a light and they thought, at the time, they thought waves, light was acted like a wave mainly. They thought, okay, well, it's a wave, okay? And the higher the energy, they would, then what would happen is electrons would be released here. Okay, so we'll draw some electrons in green here from the metal. Okay. So we have this light source. Oops, let's go back to blue here. And we have electrons being released from the metal. Okay, so this is a photoelectric effect. If you different metals had different characteristic frequencies of light. So what they found out was a couple of things here. According to classical physics, I'm going to type this so it'll be neater here. So they shone this light, and then these electrons were released, but they only were released at particular, once you get to a high enough frequency. Okay, so we'll summarize it underneath here. Okay, so according to classical physics, that light is a wave. Okay. The electrons released from the metal as the light shines on them should take some time, or should, well, we'll say first of all, we'll do the first part, should increase with the intensity of light. Okay. And then the second thing, they should be released at low frequencies of light after some energy has been built up. This did not happen, obviously. Okay, what actually happened here, there's 5 things, and we'll summarize them, but I'll just read them out to you in my little notes here about the photoelectric effect. Okay, the first thing that happened is electrons were emitted immediately when the light hits the surface. There was no time for the electrons to build up energy. Okay, there is a threshold frequency. The light shining on the photoelectric surface, the metal there, the cathode, is below a certain value, no electrons would be emitted, no matter how bright the light was. Okay? Every metal had its own threshold frequency. Okay? The light is at or above threshold frequency. The energy of the emitted electrons would increase after that, like they predicted before. And if the light was above the threshold frequency and the intensity of the light was increased, the number of electrons would also increase. So what observations they took, so we'll put that underneath here, we'll summarize those in point form. The observations in the late 1800s, first thing they said, electrons were emitted immediately when the light shined on it. Emitted is when we only one. As soon as the light shone on metal, let's say, it's that no buildup time was seen. Or energy was needed. Puzzled them a little bit. Second thing is, there was a threshold frequency of light. Let's spell that right here. That means you have to have, it had to be of a certain frequency, okay, to get this photoelectric effect. Too low, of a frequency, no effect would be observed. Even if the intensity was high. Okay. And once you hit the threshold frequency, it would then shine. Every metal had their own threshold frequency. Okay, and characteristics. It was a characteristic of the metal, obviously. The light that let's see, what was it? If the light was at or above the threshold frequency, the energy of the emitted electrons will increase as the frequency of the light increased. After threshold frequency, the light, or the electron, sorry, not the light, emitted would increase with an increase in intensity. Okay, and finally, the last one there, if the light was above the threshold frequency and the intensity of the light is increased, didn't I just say? Oh, no, the number of electrons would increase. So it would be the energy. It says after the threshold frequency, the electrons emitted would increase with, so that I did that one already. And then it said, let's just add this one to this one as well. Energy in the electrons would increase. There. Okay, so this was puzzling because they expected a nice smooth, the brighter the light, the more you should see coming off that plate of metal. And then yet some metals you would take green light or whatever of a certain frequency, put it on there and nothing would happen. You take another metal, put it there with green light, and all of a sudden, boom, you got the photoelectric effect. So it depended on the frequency of light. You have to be at or above this threshold frequency, okay, to get this photoelectric effect. So how they explained it was Einstein explained it using Planck's quantized theory. So he said, well, if you think of light as quantized packets of energy, okay, light is released in packets, not in a single continuous flowing wave, then this would work, okay? So let's flip the page here. So just a little bit of, well, let's actually draw a couple of diagrams. So if we were to draw what I'm talking about, so if we're talking about we'll just do three things here. Okay, if we call this the bottom here, we call this the let's call it the frequency. And that's over here is the current flowing, or the electrons released. Okay, you'd have nothing, nothing, nothing. You'd have zero. Let's see, blue here. You'd have zero until you hit the threshold frequency. Actually, it doesn't go like that. It goes like this first. It's been a while since I thought about this. And then it jumps up. Okay, so then at the threshold frequency, it would jump up, and then it would increase. And this is a frequency 0, which they call the threshold. Okay, so that current would increase as you increase the frequency, but you have to be at some threshold, otherwise you'd have nothing. Okay, the other thing that you saw that if you were below, so we'll say if you were below the threshold frequency, your current versus your intensity okay, you would have nothing, right? Your current would be 0 if you're below the threshold frequency. Once you go above the threshold frequency, current is I, so I'm going to use I. You would just see this. Okay, so it kind of jump up and then it would follow that. Okay, so Einstein came along in 1921. He won the Nobel Prize for explaining how light was acted as quantized energy, which we now call a quantized packet of light, a photon. Okay, so it actually happened in 1905 when he started this theory out, and he worked on it, and then Einstein. Oops. There we go. Explain this photoelectric effect by saying light was quantized. Quantized. I don't know how to spell quantized either. Not quantified. Let's say light was quantized. That means released in little packets of energy. Okay, we call these units call them photons of light. So sometimes they've got particle properties, and sometimes they have like wave properties as well, depending on where they are. So that's where quantum theory comes in. He won the Nobel Prize in 1921. Okay, for doing that. Okay, and so basically he was able to explain, okay, well, how did that actually explain this? Okay, well, what he said then, and I'll read you the little bit about the explanation in my background here. He said that, okay, first of all, these were puzzling observations. It's not what was expected from light as if it was wavelength. Okay, then it says, where is it here? How did he explain the threshold frequency? Einstein gave the explanation of the photoelectric effect for which he received the 1921 Nobel Prize. Einstein explained the photoelectric effect by extending Planck's quantum hypothesis. Einstein said that light energy was not transferred continuously and evenly as a wave would, but instead was transferred in bundles. Okay, so the explanation. Can't spell it all today. Okay, light was not transferred evenly, continuously, like a wave, but in fact, it's transferred in small bundles. Called photons. And the energy of a photon, there's a couple equations that we can use. You have to remember a little bit about the universal wave equation and stuff like that. So the energy of a photon, okay, if we say energy is equal to, we use Planck's constant without the n because it's just whole numbers here. So if we use that, okay, there's Planck's constant. Energy and frequency of light, frequency of the remember, that's the frequency of the vibrating particles. Okay, that's from Planck. Einstein extends that, and he throws in, if you remember that for speed of light, universal wave equation, velocity is equal to wavelength times frequency from grade 11. If we think of it as speed of light for c, we can just simply say that the frequency is equal to c over the wavelength of the light. So we can plug this in for f. So okay, this is speed of light, which remember is constant in all frames of reference. This is the wavelength of light, and this is the energy in a photon. Okay, and that's still Planck's constant right there. Okay, so since these two are constants, okay, Planck's constant is a certain number, speed of light is a certain number, we can write it as this, and we'll use something called an electron volt, and I'll explain what an electron volt is right away. It's 1240 electron volts divided by its wavelength per nanometer. Electron volts times nanometer. That's the wavelength of the over so many nanometers. Okay. So. Okay. This is the energy of a photon. Photon. This is the wavelength in nanometers. Okay, so nanometer is times 10 to the negative 9 for nanometer. Okay, so what is an electron volt is what you're going to say. Okay, so 1 electron volt equals the charge on an electron times 1 volt. So 1 electron volt is equal to about 1.60 times, we're going to just do 3 figures here, times 10 to the negative 19 joules per electron volt. Okay, so if we wanted to change that to joules, we could. Okay, so I'm going to pause for a bit here because we got a bell going here, and we're going to have O Canada and a few things here this morning, and then I'll finish off by this lesson in the last 10 minutes or so by doing an example question or two using this idea of the energy of a photon. Okay, sorry about that. So let's just this will be our last thing. There is a couple other quantum things here, but I think we're gonna, that we could look at, like quantum scattering, and we could look at the more mathematical approach to it, but it's not really that important for us to do all of those types of things. In fact, I'll just kind of lead into that a little bit and tell you what it kind of means. But let's do an example of this energy of a photon here, and also using this conversion here with an electron volt equaling a certain amount of, right here, electron volt equaling 1.60 times 10 to the negative 19 joules. Okay, so let's do a couple examples like that, and then we'll call it a day, and then we'll pop up and the hand in for this unit. This unit will not have a quiz on it. It'll just be on the final exam. So you won't have to worry about doing a short quiz here. And then we should still have, right now here in Vanguard, this is June 1st, and that should give everybody those extra 2 to 3 weeks to finish, depending on how spread you are. You might be right with me, you might be behind a little bit or whatever, so that's fine. And you'll have that little bit of extra time at the end here in June to kind of get caught up on all your online stuff. Okay, so let's take a look at an example of that. So let me find one here. Okay, so what is the photon energy? Okay, so let's say what is the photon energy for a 550 nanometer light source? What is this energy? Joules. Finally, our last one. Let's try. What is the wavelength of? We'll do that one next. Let's just work this out first. So obviously, if we're going to be using energy of a photon, traveling at the speed of light, obviously, because it's light. Okay, energy of photon, we got 1240 electron volts divided by the wavelength. So in our case, it's 1240 divided by electron volts per nanometer, sorry. Okay, and then we divide that by 515 nanometers. Okay, and we'll get our energy, so nothing really difficult here. So 1240 divided by 515. So we end up getting 2.41 electron volts. Okay, and then if we want to change it into joules, 2.41 electron volts times 1.60 times 10 to the negative 19 joules per electron volt. So I'm just going to round it off after. I'm just take my calculator, multiply by 1.60 to the negative 19. So I get 3.85 times 10 to the negative 19 joules of energy. Okay, and then should do a reversey one, and that'll be it for physics this year. That'll be our stopping point. And then I'll put a hand in up that you can work on as well. I just have to finish typing it out. Okay, so let's try one with finding the wavelength. Okay, what is the wavelength of a photon with an energy of, put it in joules, so we have to do the conversion first. Let's say 5.2 times 10 to the negative 19 joules. Okay, so in this case, we're first going to have to convert this into electron volts to use the formula, because the formula is in electron volts. So we got to change the energy to electron volts. So this way we go 5.2 times 10 to the negative 19 joules. Okay, and this time we want to get it into electron volts. So we're going to divide by 1.60 times 10 to the negative 19 joules per electron volt. And that's going to give us how many electron volts we have. So take 5.2, exponent at negative 19, divided by 1.6, exponent negative 19, and we get 3.25 electron volts. Okay, and then we can use our formula. So our formula is energy equals 1240 electron volts times nanometers divided by wavelength. So in this case, we want to get the wavelength. So we have to rearrange this. So if we multiply the wavelength out here and then divide by E, this would be, let's put 1240 electron volts per nanometer divided by the energy. Okay, so in our case, that's going to be 1240 divided by 3.25 electron volts. That's going to give us our frequency of light. So go ahead and do that. 1240 divided by 3.25. So 381 nanometers, 381.5, so 380 to two significant figures, nanometers, because the original one was only two significant figures, is our wavelength. Okay, and that, we'll say, is the stopping point for the modern physics unit. There is a couple ones that I could extend here. We could have talked about another thing that Einstein said was, he said that a photon should have momentum. So they talk about something called the Compton effect, if you want to look that up as well. But we don't necessarily need to go that far. And then something called the work functional as well. How much extra energy do you need to push it out? So if the electron is embedded in the metal, you'll need a certain amount of work to bring it to the surface, and then you can release it. But again, that's another one. And then there's something called de Broglie waves, which give you that Heisenberg's uncertainty principle that you might have heard about, which is where they say, well, the uncertainty principle is considering you can find how much you can measure the momentum of this particle, but then you can't find its location. You're not sure where its location is. or you can find exactly where it is, but you're not sure what its momentum is because of the uncertainty principle that it involves. But at this point, I think we'll stop here for physics this year. Okay, so I'll put up a little assignment, and you can work on that, and that'll be the last thing to hand in. And then for the final exam, there'll be a summary of what to expect on the final exam. And you can make a formula sheet up for yourself, cheat sheet if you like, 8.5 by 11. Put anything on it that you want. So good luck with that.